Hello everyone. My name is Asawar Bin Riaz, and I'm part of the system design team at Beko Cooking Appliances Plant in Bolu, Turkey. Today, I'll be presenting our work titled Feasibility of Using Computational Fluid Dynamics for Simulating the Performance of Cooling System for Induction Hobs. This study was conducted together with my colleague, Yeet Akin Chibarlu. In recent years, induction hobs have become increasingly popular because of their high energy efficiency compared with gas or electric cooktops. However, they rely heavily on power electronics, especially IGBT modules, which generate substantial heat during operation. Therefore, effective thermal management is vital to ensure reliability and prevent component degradation and extend the life of the product. In this study, we are using CFD tools. Computer fluid dynamics, or CFD, allows us to simulate airflow and temperature distribution virtually, enabling design optimization before physical prototyping. In this study, we investigate how accurately CFD can predict the real-world cooling performance of an induction hob. The objective of this work was threefold. Firstly, we wanted to develop a CFD model for an induction hobs cooling system. Secondly, we wanted to simulate the installation environment by placing the hob inside a standard kitchen cabinet. Thirdly, we wanted to validate the CFD prediction with the experiment results. Ultimately, our goal was to determine whether CFD can be a reliable design tool for thermal management in home appliances systems. This project analyzed a 4-zone induction hob, which uses 2 heat sinks and a radial fan to cool the power electronics. Here, the heat source, the IGBTs, are placed on the heat sinks, and the fan blows air across the heat sinks and exhausts them through the front grills to cool the internal electronics. Here, the hob was modeled inside a standard kitchen furniture to reflect a real-life operating condition. This approach is important because air recirculation and space confinement inside the cabinet have a major impact on the cooling efficiency of the hobs. Our heat source were the IGBTs. Each IGBT module was modeled according to its TO247 package structure. We treated each device as a volumetric heat source by applying the condition on the silicon die. We accounted for both the conduction and the switching losses. To balance the accuracy and the computational cost, we adopted a hybrid modeling approach. We simplified the actual geometry of the IGBT, but we kept the essential internal layers like the silicon die, the copper frame, and the resin encapsulant. The IGBTs were mounted on the heatsink via a thermal interface material, which represents the realistic heat conduction path in the hob. The setup allowed us to accurately capture the main heat transfer mechanisms while keeping the computational cost manageable. The CFD domain included both the solid regions, like the heatsink, chassis, and the electronics, and the fluid regions of the air. The radial fan was modeled using 2 steady-state approaches, the frozen rotor and the mixing plane methods. The frozen rotor method assumes a stationary blade region in the rotating reference frame, while the mixing plane method averages flow quantities between the rotating and the stationary domain. The latter provides better flow continuity and similar accuracy to the transient simulations, but at a fraction of the computational cost. This made it ideal for our induction hob case. For meshing, we generated a high-quality mesh of about 16 million cells, including the inflation layers around the fan blades to resolve the boundary layer accurately. The simulation used a steady-state k-omega turbulence model, and for convergence, we were able to achieve the following values for the continuity, momentum, energy, and turbulence kinetic energy residuals. These settings ensured numerical stability and physical accuracy of the predicting the airflow and the temperature fields. Here we will compare the two fan models against the manufacturer's specifications. The frozen rotor method predicted a flow rate of 0.54 meter cube per minute, while the mixing plane predicted a 0.93 meter cube per minute flow rate. The datasheet value provided by the manufacturer for this type of fan was 0.78 meter cube per minute. When we look at the error rates, the mixing plane approach achieved around 19% error, compared with the 30% error for the frozen rotor model. The mixing plane also produced a more uniform velocity field, as you can see in the image, which eliminated the unrealistic flow separation near the boundary between the rotating domain and the stationary domain. Based on these results, the mixing plane method was selected for the full system simulation to maintain accuracy and achieve computational efficiency. The figure here on the bottom right shows the temperature distribution across the IGBTs and the bridge diodes for both the CFD results and the experiments. As expected, components closer to the fan outlet were cooler, while those further away from the fan were hotter. CFD prediction matched the experimental temperatures between 8 to 20%, which is a very good range considering the complexity of the system. The deviations from the experimental results are mainly due to the simplified heating assumptions that we made for the IGBT heat source and the aluminum plates that house the coils. Overall, this confirms that the hybrid IGBT model accurately captures the primary heat transfer pathways. To summarize, CFD accurately predicts the temperature trends and airflow patterns in the induction hobs. The mixing plane method significantly improves fan modeling accuracy, and the hybrid IGBT model offers an excellent balance between accuracy and computational efficiency. Therefore, we can say that the CFD can confidently be used for early design validation, which will reduce the need for multiple physical prototypes and eventually speed up the design process. In conclusion, our CFD model achieved about 80% agreement with the experimental data, validating its feasibility for design use. For future work on this kind of cooling design simulations, we plan to perform transient analysis, taking into account the power reduction software involved with these kind of products. And we will also explore alternative fan and heatsink designs to ensure cooling performance and reduce the noise. This modeling approach can ultimately contribute to quieter and more efficient and reliable induction hobs. These are the references that we used in our study. I won't have time to go over all these individually, but these form the basis of the theory, which I presented to you in this presentation. This concludes my presentation for today. Thank you so much for your attention and for this opportunity. If you guys have any questions, I'm here to answer them.